Hi again, everyone. My name is Shir, and I'm a data science team leader at Intuit. And today I'm going to talk to you about something a little different, about how to find a needle in a haystack. Or specifically in our case, how to detect anomalous behavior within your systems. So we're going to review the problem we're discussing, the data, and present an adjustable and generic anomaly detection framework. 2 examples of the models generated by this framework. So what is our problem? As you know, I work at Intuit. Intuit is the global leader of finance management software. We have many products. We have TurboTax, which helps 60% of the Americans file their taxes every year. We have QuickBooks for small businesses and Mint. And all of these applications use many services across Intuit. Each service uses many production services. The behavior of these servers is comprised of many actions the server do. They ask for data for the database, they move data from place to place, etc. And this behavior changes according to different sources. It changes according to user behavior, according to the code, and code changes. Our goal is to detect whether something weird has happened, whether there's some anomaly. Okay, so what is the data we work with? We have a centralized system which tracks all of these servers live, and it collects all the data about the different actions that each server does. As you can see here, it looks like this data frame with each service name and the different action name, and we pre-process it to a time series of the number of actions at each minute for each service. The requirements for our system is it should be very fast and accurate. It should give us anomalies right on time in a minute resolution. It also has to be very generic. As you can see from the plots here, we have different types of time series which are very dense, time series which are very sparse. We have different kind of periodicities. Weekly periodicity, daily periodicity, yearly periodicity. We also have dependency on external sources, for example, tax submission date, if it's for TurboTax, or different patterns in user behavior, holidays, server behavior. And we also need for the system to be very adjustable because we have to be able to consume new time series and new actions all the time and also be able to handle different changes in the time series behavior. So this is the framework we suggest. Given a list of available features based on historic patterns within the time series, external data sources, and similar series of other actions which are correlated with this series, and also a list of possible modeling approaches, we build a whole framework around it. The modeling approaches we use are a few linear models. Among them you can find Huber-Regressor, which is best in dealing with the outliers. Lasso, which is very good in feature selection, and ElasticNet, which comprises between Lasso and ridge regression. And we also use some nonlinear models, such as K-nearest neighbors, which we'll show an example for later, and ActiBoost, which is an ensemble of regression trees. The framework works in 2 stages. The first stage is fit. The fit stage makes this system adjustable. What it actually does, it's every day for each series, we train a new model. We select what is the most appropriate model for this series based on the historical data we have so far. We select the best features for this time series from all the features that we can see above, and also calculate the confidence interval around our prediction. Once the value getting at a point is beyond the confidence interval we calculated, this will be an anomaly. So this happens every day. Every minute we do the predict stage, which does a prediction and then raises anomalies. Based on the selected features and the trained model in the fit stage, every minute we get a new time point. We calculate what is the prediction. And if the true value is too far from our prediction based on the confidence interval derived during the fit stage, we raise an anomaly. So a bit visualization of how this actually looks like in the flow. We have historical data in the fit stage, which is all the data for a specific action until this day. we put it into some feature generator, which generates us this data frame you see here. The data frame contains the time points of the historical data. The target is what we want to predict. This is our Y vector. And all the rest are features. What happened in the minute before, what happened 17 minutes before. These are historical features. Also aggregation of what happens in 2 hours before, 3 hours before, in the days before. What happened in a similar series, or also in similar series with lags. Maybe we have correlation between different times in different series, and etc. Then, based on the historical data, we divide the historical data to 2 parts, a training period and an evaluation period. We train our model on our training period and evaluate it on the evaluation period. And we train a few models, as I said before. Then we select which is the best model, and we do stepwise feature selection, meaning that at each stage we eliminate some of the features in order to use as less feature as possible to get the leanest and not overfitted model. Then we generate some trained model. It could be a linear model or non-linear model, which we have for the rest of the day. And in predict stage, we get a new series of data, maybe 1 point, maybe a few points. We get all the external data sources. We generate the features with the same feature generator. And then the predictor, which received this generated data set for the new data, creates a prediction and compares the true value with the prediction. If the true value is too far, then we raise an anomaly. The confidence intervals can be determined by a couple of ways. One of the ways to determine it is using the errors during the evaluation period, the errors of the prediction versus the true value. We look at the distribution of this error, and by that we create a confidence interval. Here you can see an example of the resulting linear model. In the top graph, you can see the service 1, action 1 prediction in green and true value in blue. And the black line is the high bound resulting from our system. As you can see, if the blue line will cross the black line, we will raise an anomaly. On the bottom, on the 4 bottom plots, you can see the coefficients, the strongest coefficients for this linear model. The top plot shows that the strongest coefficients is actually what happened in the minute before in this time series, because there is probably some smoothness in this time series. The second and third features are actually other actions in this service which are correlated with this action. So we actually use other actions to predict what should be the value in this action based on the correlation between them. And the fourth feature is just a summary of what happened in this time series an hour ago. So as you can see, it's much smoother because it summarized the amount and log per hour. A second example of a model, it's a non-linear model, which also incorporates a way to calculate the confidence intervals within the model. How does it work? K-nearest neighbors, for a certain time point we want to predict, find the most similar pattern in the past of the time series, as you can see in the train vector. It finds K-nearest neighbors, for example, K is 20, so we find K similar patterns in the past of this time series based on the features we saw before. Then the prediction from these K nearest neighbors gives us the distribution of values of what should be our predicted value. This distribution and value you can see from the right here can provide us also a way to define the confidence interval of our prediction based on the distribution of the K nearest neighbors. Let's see an example of how this works. So here the red line is the true value. The green line is the median of the K nearest neighbors, and the black lines are the prediction bounds, the confidence interval bounds, the maximum and the minimum. And here they are generated from the distribution of the nearest neighbors. So as you can see, they change all the time. They are not constant about the prediction as we saw before. So to summarize, we saw an anomaly detection framework which is generic because it uses many models and many combinations of features, and also adjustable because it fits itself every day. Also, we have flexible architectures. You can plug into the system different types of features, different types of external data sources, and also different types of models. And we saw how to derive statistical bounds to give anomalies on real time. That's it. If you have a question, you can contact me later. Thank you.